Dear students, I am Ramesh, chemistry faculty from Vidya Mandir Metric Higher Secondary School, Uttangarai. Let us discuss crystal field theory. And here the silent features of crystal field theory. Silent features of CFT, crystal field theory. And here, according to this theory, the ligand and central metal atom is considered as purely ionic. So, the bond ligand and central metal atom bond is considered, purely ionic. Purely ionic. What do you mean by ionic bond? There is the electrostatic forces of attraction between the central metal atom and the ligand. So, according to this theory, it is purely ionic. But in the case of VBT, it is purely covalent. Now, the second postulates, we are taking the charged central metal atom and that charged ligand are considered as point charges. So, here the charged central metal atom or the charged ligands. So, charged central metal atom and that charged ligand are considered as point charges. And if it is a neutral central metal atom like nickel tetracarbonate, then central metal atom is neutral. So, if it is the neutral central metal atom or the neutral ligand is considered as electric dipoles. It is considered as electric dipoles. And the third assumption, according to this CFT, the complex formation is taken as the following steps. So, we are taking that the step 1. And we are taking the step 1 for complex formation according to CFT. And here, in a gaseous isolated state. So, here the isolated gaseous state, the d orbital of central metal atom are degenerate. So, what do you mean by degeneracy? Degeneracy is nothing but here equal energy orbital. So, equal energy orbital is considered as degenerate orbital. So, all the d orbitals are degenerate orbital in isolated gaseous atom. And here the ligand approaches the x and y and z axis. So, here we may take that the ligand forms a spherical field. Ligand forms a spherical field around the central metal atom. So, here we may take that it is a central metal atom. Now, we may take the ligand. The ligand form a spherical field around the central metal atom. So, it will be, a ligand is considered as a negative charge. So, it is an electron donor. Now, what happened here? The d orbital energy in that degeneracy or degenerate orbital will increases. So, all the d orbital energy, so here the energy of d orbital increases in a spherical field. So, here we may take in a isolated gaseous state the d orbital as degenerate orbital. And ligand form a spherical field around the central metal atom. So, what will happen here? The energy of d orbital increases because the electron-electron repulsion between the ligand and the central metal atom. So the energy of d orbital increases because the electron repulsion between the ligand and the central metal atom. Now we are taking that is a step 2. So step 2, we may consider in a octahedral spherical field. We are taking that the octahedral spherical field, and we may consider a cube here, octahedral spherical field. We are taking that the cube, and in a cube the central metal atom is present in the origin. The central metal atom is present in a origin. So here there is a central metal atom. Now here it is x-axis, and here it is the y-axis, and here it is the z-axis. Now we are taking that the octahedral field, there are 6 ligands. So here in octahedral complexes, there are 6 ligands. So here there is a 6 ligands, and these 6 ligand approaches x and that x dash, and it is minus x, y and that minus y, z and that minus z. So in octahedral complexes, 6 ligand approach the central metal atom in x plus x minus x plus y minus y plus z and that minus z. So the central metal atom will approach us like this. Now consider here the central metal atom as a d orbital and the d orbital shape. So here we are taking the d orbital. And what are the d orbital? They are, that is d xy, d yz and d zx. And what is the shape of a d orbital? These all are clover leaf shape. It is the clover leaf shape. It is a clover leaf shape, and here it is a x and that y and that y and z and that z and that x. So all are same shape, then it is a clover leaf shape, and the leaves are present in between the axes. So here the leaves or clover leaves are present between the axes. And so this is clover leaf shape and between the axes, and these are considered as T2G orbital in CFT. So in CFT, T2G orbitals are dxy, dyz and dzx, and these T2G meaning it is triply. So triply generate orbital. So it is considered as a T2G. Now we may take that the another 2 orbital, we are taking that is dx square minus y square. And what is the shape of this orbital? We are taking that is a clover leaf shape. It is also clover leaf shape along the axis. So here it is clover leaf shape along the axis. So here this dx square minus y square is clover leaf and along the axis. So it is along the axis. Now we are taking dz square orbital. And dz square orbital, we are taking that here it is a z-axis, and it is dumbbell with drought nut at a center. It is a dumbbell with a drought net at a center. So we are taking these dx square, y square and dz square orbitals are considered in CFT. They are Eg orbital. So in CFT, the d orbital is considered as T2G and Eg. T2G means triply generate and Eg means equally generate. Equally generate orbital. Equally generate orbital. So according to CFT, we may take that the d orbital may be splitted into two types. One is Eg and that T2G orbital. Eg and that T2G orbital. And up to this point, the complex formation is not occur. The complex formation is not occur. When the ligand approaches further, so we may take that it is a step 3 and the ligand approach further. So the ligand approach further and there will be an attraction between central metal atom and the ligand and make a ionic bond. So the ligand approach further, the attraction between central metal atom and that ligand. Central metal atom and that ligand. And this attraction will decrease the energy. So the attraction leads to decrease of energy. So after that, the complex is formed. So complex is formed. So we may take that in crystal field theory. The first one, a central metal atom is surrounded by a spherical field. So that the energy of d orbital is increases. And if you are taking the second one, when ligand approaches, the d orbital will be splitted into two types. One is T2G and Eg. And after that, up to this point, there is no formation of a complex. There is no formation of a complex. And here, further approaching, here there is a attraction between central metal atom and that ligand. So the energy of central metal atom and that ligand decreases. So the complex is formed. Now, crystal field splitting in octahedral complexes. So first we may take the d orbital. So the d orbital as degenerate orbital. So it is a d orbital of a central metal atom in a isolated gaseous state. Now what will happen here? Here the ligand form a spherical field. So that due to electron-electron repulsion between that ligand and that central metal atom, here the energies of d orbital will increases further. So here the energies of d orbital is increases. So it is a normal energy. And in a spherical field, so it is the average energy of a spherical field. So average energy of a spherical field. So average energy of d orbital in a spherical field. Now further the ligand is approached. What will happen? So the degeneracy of d orbital is vanished. Degeneracy means equal energy orbital. And the equal energy orbital further splitted into two types. In octahedral complexes, what will happen? Here, the dx square y square and dz square orbital. So here, dx square y square and dz square orbital are considered as, what is that? It is Eg orbital. And these Eg orbitals are present along the axis. So the Eg orbitals are present along the axis. So along the axis, the Eg orbitals are present. So the electron-electron repulsion along the axis is increases. Why? The ligand approaches the central metal atom along the axis. So along the axis, which d orbital is present? Eg orbital is present. So the Eg orbital increases. The Eg orbital increases by 3 by 5. So here the Eg orbital increases by 3 by 5. So the energy increases plus 3 by 5 delta naught to compensate the delta O. So here delta O, the energy of an octahedral complexes. So Eg orbital energy increases by 3 by 5. Now we may take the T2G orbital. What are T2G orbital? Here dxy, dyz and dzx are considered as triply degenerate orbital, and the T2G orbitals are present between the axes. Between the axis. So here between the axis the T2G orbitals are present. So the ligand approaches along the axis, that is x and y and z axis, and here the T2G orbitals are present between the axes, so it experiences less repulsion than that of Eg orbital, so that the energy decreases. The energy decreases. So here the energy will be decreases by, that is 2 by 5. So here 3 orbital energy decreases by 2 by 5, and here the Eg orbital, so the Eg orbital energy increases by 3 by 5, and it is T2G energy orbital decreases by 2 by 5. So it is the crystal field splitting in octahedral complexes. Now we may take the crystal field splitting in tetrahedral complexes. So here the crystal field splitting in tetrahedral complexes. Tetrahedral complex. Listen, in a tetrahedral complex, we may consider a cube. We are taking the cube. In a cube, the central metal atom is present at the center of the cube. So here there is a central metal atom. And the ligands are approaches alternate corners of the cube. So here the ligands are approaches alternate corner. So here L1, and here another one ligand, and here another one ligand, and here another one ligand. So the ligands are approaches alternate corner of the central metal atom. Now it is x and y and z axis, correct? So here it is the x axis, and here it is the y axis, and here it is the z axis. So here the central metal atom, and we are getting the tetrahedral in shape. And if it is the central metal atom in that origin, then the ligands are approaches to central metal atom. So here we may take that none of the d orbitals are very close to the direction of the ligand. So here the ligand approaches, and here the ligand approaches on that y and x and z axis. But here the ligand is present here. So the d orbital, none of the d orbital is very close to that the ligand approaches. But however here the T2G orbital. So the T2G orbitals are very close, that is the direction of approaching of the ligand. So the T2G orbitals are very close to the ligand approach. So what will happen here? The T2G orbital. So what are T2G orbital? Here the T2G orbitals are d xy, d yz and d zx. So this energy increases 2 by 5. So here it is very close to the ligand approaching side, so that the energy of this T2G orbital increases by 2 by 5. So here the EG orbital, what is that? dx square y square and that dz square orbital, the energy is decreases by 3 by 5. Delta T and here delta T. So we may take that here the d orbital in a isolated state. Here it is a d orbital in a isolated gaseous atom. Now it is a degenerate orbital. Now the energy will increases somewhat in a spherical field. So the energy will increases. So it is the average energy in spherical field. Average energy in the spherical field. Then here what will happen? Here it is a delta T. Now this is, here we are taking the T2G orbital. T2G orbitals are, that is 3 orbital. The 3 orbital energy increases plus 2 by 5. And here the EG orbital energy decreases by 3 by 5 delta T and here delta T. So here that is EG orbital. So it is EG orbital and it is T2G orbital. So we may compare the octahedral field and the tetrahedral field. It is reversed. And comparing the delta T and the delta O, we may compare the delta T, crystal field splitting in the tetrahedral complexes and crystal field splitting in octahedral complexes. And it is always delta O is greater than delta T. So crystal field splitting in octahedral complexes will be greater than that of crystal field splitting in tetrahedral complexes, and it will be related delta T, which is equal to 4 by 9 of delta O. 4 by 9 of delta O.